So welcome back, everybody. The topic this week is roughly what we were also supposed to cover last week, but instead of recording the lecture, I thought that we could actually discuss these topics a little bit more in detail together. So one of the things which I would like to do today is actually to wrap up the discussions on solving differential equations with neural networks and deep learning methods. And this is something which some of you may be interested in following up for project 2 and also project 3. Then we are going to look at what's called convolution neural networks, which is one of the, one of the main methods in for instance, imaging and recognizing different types of images. And this is a very important development within the field of deep learning, and which has had very important consequences for many fields. This spans from medical imaging to simply recognizes faces. Now, the one of the things which I also wanted to quickly present to you before we move on is a brief discussion of project number 2 before we move on. So if you go back to the basic link where we have the teaching material, so you can see now roughly what are the plans for the time to come before we meet physically on March the 7th, is both a discussion on further deep learning methods. But then if you scroll down here, you will find a outline of project number 2. So one of the things which I would like to ask you about is whether you could come with input to alternatives to project number 2. So if we take a look at the project number 2 here, what I did was also to put a deadline of April the 2nd. So we're always flexible with these deadlines, as you probably have realized. So you can, if this is of interest for your research, you can propose your own data set, which aligns better with what you are doing. Alternatively, there are data sets both from the University of California at Irvine, there is Kaggle.com, and many other types of data sets. So just to give you an example, people who do high energy particle physics, there is an excellent data set on finding the Higgs. That's a kind of challenge which people at CERN have been placing there for years, since actually 2014. Now, one of the things we would like you to do then is the following. And there are actually many alternatives, and you can tweak the various alternatives for project number 2. So you can, if you have your own data set, the methods which we have been covering, and today we're also going into convolutional neural networks, and next week we're going to cover recurrent neural networks. We have been discussing linear regression, logistic regression, neural networks, support vector machines. We've been looking at decision trees and other methods. And the if you wish to combine these methods, you should at least have 2 of them included in the analysis of data. And this is pretty common when you analyze machine learning data. You could, if you are more interested in a statistical analysis, you could, for instance, take some of these methods and study the bias variance trade-off on a specific data set. So you should feel free to propose alternative to what is sketched here. The basic structure of the report, as you can see, follows the kind of setup which we had for the first project. We have an essential part where you discuss the data, you discuss how the data are produced and place them in a proper context. You need to include at least 2 central algorithms, or as an alternative, explore methods from, let's say, decision trees and so on. You can then describe your algorithm and its implementation and tests you have performed. And then you would typically present results and findings and so on. The exercise, or what you might say, the type of a project which we propose for those of you interested in differential equations, is actually to solve the standard diffusion equation, which we will discuss a little bit more in detail today. Just remind you of some of the basic methods which are used to solve it. And then the first part deals with a standard implicit or explicit scheme, which is one of the most common approaches for solving this one-dimensional diffusion equation. And after you're done with that, you have the basics for the standard solver for diffusion equation. And then the next step is actually to compare the solution of the neural network with the standard approaches. In this case, the standard approaches are given by an implicit and explicit scheme. And part D is obviously a critical assessment. When you're dealing with the solution of the diffusion equation using neural networks, you will notice that the codes which are online, they are not written with an efficient library like TensorFlow with its API keras. And that means that if you're interested, you could, and you want to speed up your program and use a deeper network, I would normally recommend to solve a differential equation using, let's say, for instance, TensorFlow, or if you're more familiar with PyTorch, you can use PyTorch or similar libraries. So the project 2 has one, what you might call the default variant, which is solving differential equations with the neural networks. And then it has a more optional variant where you can define your data set, and then you need to use at least 2 of the methods which we have been discussing in order to analyze the type of data set. And this is where you can really tailor this project here to your own research. And a typical situation could be to use deep learning methods to analyze the data which you have been studying in your own research. So feel free to come with suggestions, and just view this as a very flexible path for project number 2. So there is a default one with ordinary differential equations, and then we have the one which deals with you proposing a data set and methods you would like to analyze. For those of you who are following more statistics path, there's also the possibility, which I think is very interesting, to do a statistical analysis of the results you would obtain with different types of methods. And one of the things which, if for those of you which are most interested in that kind of path, would be to, for instance, perform a bias variance trade-off analysis of, let's say, neural networks. It could be support vector machines, standard linear regression, and come up with a critical assessment of how these methods perform for a given data set. Okay, so feel free to ask questions. You can unmute yourself, or you could just ask questions in the chat about the project. We can also chat about this during the break. If you don't have any questions, I would like to move back to the topic which we have been discussing during the last time. And I wanted to remind you quickly of some of the basic elements. So in order to do that, I'm going to switch to my Jupyter notebook. So let me do that immediately. So what we have been doing, so if we scroll back a little bit, where we ended last time was in our discussion of the Poisson equation. And the basics of solving a differential equation or a partial differential equation is with neural networks is actually to, so the equation we were looking at last time was the Poisson equation in one dimension. This is an equation which has been stripped of all the physical constants of the system, and we end up with simply a second derivative, which is now equal to a function f of x. Now, this is a so-called 2-point boundary value problem, and we have defined x to be between 0 and 1, and we have the boundary values of at 0 and 1, which we have simply fixed to 0. So these are so-called Dirichlet boundary conditions. And then we defined a function, f of x, which is a function which can which allows us to get an analytical solution. And what we did when we study neural networks and apply neural networks is that we need a trial wave function which obeys the boundary conditions in this case, alternatively initial conditions. And when we move to ordinary differential equation or partial differential equations, we will need to satisfy both boundary conditions and initial conditions. Now, in this case, we have only boundary conditions, which are given by these two values. And then we plug in a trial solution, which now satisfies the boundary conditions and is given by the neural network. And the analytical solution in this case, so what we are looking at is actually, we are now peeping into the analytical solution, which is given by this function. So we are trying to guide the neural network to have some of the properties of the analytical solution. And in what you can see here is now that the neural network is supposed to, in a way, to take into account the exponential function. Now, when we did this, what we ended up with when we solved the neural network problem is that we take the difference between the left-hand side and the right-hand side of the differential equation, and we square that difference, and that defines our cost function. And we start the calculations with a trial function, and then we let the neural network gradually try to find the best possible representation of the function which is missing here, which would be the exponential function. So you can do that with autograd, as we've seen from these examples, which we discussed last time. And autograd is very convenient because it allows you to compute efficiently the derivative of the cost function, because that's the function we want to minimize. And in this specific case, the cost function is the squared difference between the left-hand side and the right-hand side of the differential equation. That's the basics of solving differential equations with neural networks or deep learning methods. Now, what I wanted to move on to now is the topic which is more coupled up with project number 2, in case you are dealing with partial differential equations as one of the options. And if you scroll down here, this is just a quick repeat of what we did last time. You can actually solve this efficiently by using a linear equation solver. This algorithm is actually, since you end up with a tridiagonal matrix, this algorithm is called Thomas algorithm. So the examples here were roughly the examples where we ended last time. And what I wanted to do now is actually to start with the partial differential equations and link this up with the diffusion equation. So a partial differential equation is, as you know, it's a differential equation which has a dependence on several variables. The case we are going to look at is a diffusion equation in one dimension. Now, in project number 2, if you are dealing with something different from the diffusion equation and you would like to explore that type of diffusion equation, which a partial differential equation which is linked with your research interests, feel free to change the diffusion equation which we are proposing as a possible path in the project with a partial differential equation which aligns with your research. So in the beginning here, you will find just a brief review of some famous partial differential equations, like the wave equation in one dimension. We have the wave equation in 2 dimensions, the diffusion equation. And what we are going to look at now is the way, the standard way by which we would typically solve the diffusion equation. And this is one of the parts of project number 2, if you're going to follow that path, which we are going to outline in the handwritten notes here. So let me, before we go back to the codes, let me now just switch back to the whiteboard, and we are going to look at the diffusion equation in 1 dimension. And this can easily be modified to 2 dimensions or 3 dimensions if you prefer that. And after we're done with this, we are going to move over to convolution neural networks, which is one of the favorite methods if you're dealing with imaging and image recognition. Okay, so feel free to ask questions, but now what I'm going to do is actually to move over to the whiteboard, and we are going to look at the diffusion equation in 1 dimension, which is the one which is relevant for project number 2. So let's just set up the basic mathematics. And there are 2 schemes which are widely used. So let me just bring it up in 1D. And the schemes we are going to look at is the first scheme, which is called the explicit scheme. And then we have the implicit scheme. And these are 2 widely popular schemes which are used in these type of differential equations. The first scheme is going to give us a very simple recipe which can be quickly implemented, but it's going to suffer from a stability criterion which is pretty strong, and it puts a very strong limitation on the choice of step sizes in the x and the y direction and the time direction. The implicit scheme is a scheme which will be stable for all the discretized time steps and steps in the x and the y and the z direction, which are relevant for the solutions here. So if we now look at the differential equation, so this is an equation which now has been scaled, and we are going to look at the equation in 1 spatial dimension and 1 temporal dimension. So it's a time derivative. There is normally a constant, which we call a diffusion constant, but what we are assuming now is that this constant has been absorbed in the rescale parameters here. So this is normally what we would call a scaled equation. We're also going to simplify life, and we are going to assume that x is defined within a region. So since this is now a scaled equation, we can now assume that it lives in a region 0 to 1. Else, this would be a region which is defined by the appropriate physical constants of the diffusion equation under study. So we're also going to assume that we have boundary conditions. So time is now going to be between 0, which will be a t0, and then some final time, which we just call for t final or tn here. So the boundary conditions are now given by, they can be given by some Dirichlet boundary conditions. And we are simply going to require now that we have a u of 0 at a time t, and we can put that one just to make life very, very simple. So we have the 2 boundaries, and we can just put that one equal to 0 for all times. And then we would have some initial conditions. And in that particular case, we would have a u of x of 0, which would now be typically given by some function which we can just call g of x. So the boundary conditions and the initial conditions are known. Now, the next thing which we will do is to discretize. And we are going to assume now that we have a given number of time steps and a given number of steps in the x direction. So we would now let x go over to a discretized x. So that will be an x of I, which is going to be given by x0 plus some I times some delta x. And we are going to let this I go from 0 1 up to some specific point, which we could call m here. And then we're going to discretize time. So we have a time tj, and that's going to be given by a t0 plus some j times delta t. And then this j is going to be defined for the different time steps we have chosen up to a final time n. So the values of these variables, in our case, since the boundary points are given by 0 and 1, so it means that this delta x now would typically be given by 1 minus 0 divided by m. So in our case, this is just going to be 1 divided by m. And then we could also define a delta t, which will be given by this t final minus t0, which is in our case just chosen to be 0. So that will be given by a t of n divided by n. So these are now constants which we use to define the problem. Then we are going to let u of x of t. So in principle, I should have used another symbol because they're not exactly the same functions, but I'm going to keep the same symbol here. So this is going to be given by an x of I and then a t of j. And we would typically write this out as a uij. Now, the next thing we need to do is actually to set up the derivatives. So we can now approximate the first derivative, du dt. That can be written with a forward moving algorithm, so which would be Euler's forward algorithm. And we can rewrite this as a u of I, and then we have a j plus 1, so we move ahead one time step, minus u of I of j divided by delta t. And then we have a plus an o of delta t. So the error in what we normally call Euler's forward stepping, or just forward Euler, that carries an error which goes like delta t. Now this can be improved by a scheme which you will find in the lecture notes, which is called the Craig-Nicholson scheme. So that's something which we can improve by adding corrections so that we end up with a delta t squared. And that will be the typical approach which we end up in most algorithms, that we try to find a balance between numerical accuracy and the number of cycles which we have to deal with in our computations. So the forward Euler scheme is actually the one of the simplest possible ways to approximate the first derivative. So what we are going to do now is to simply replace the u dt. So we replace it, and this is actually u of x of I, and then we would have a tj plus a delta t minus u of x of I of tj divided by delta t. And that's what we would typically rewrite as a u of I of j plus 1 minus u of ij divided by delta t. Now, if you're dealing with more spatial dimensions, we get more indices in these quantities u. So the second derivative, on the other hand, is approximated with another famous formula, which is called the midpoint formula for the second derivative. So in our case, this would be given by, and I'm just stating the result here, so we would have a I plus 1. So this is the same as u of xi plus delta x. It's at the same time, plus u of I minus 1 of j minus u of ij multiplied with 2 divided by delta t squared, delta x squared. And this goes plus an o of delta x squared. So the error which we carry with us comes with a delta x squared times some constants. So if delta x is pretty small, then what we hope for is that we can neglect these higher order corrections. So this means that what we are going to do now is a u of I plus 1 of j plus u of I minus 1 of j. And these expressions which you have here, they're just given by plain Taylor expansions. So this is a manipulation of a Taylor expansion, and you can obtain the expression for the famous expression for the second derivative. So this means that our differential equation now, which is a differential equation in time and space, this goes now over to u of I of j plus 1 minus u of I j divided by delta t, and this is equal to u of I plus 1 of j plus u of I minus 1 of j minus 2u ij, and this is divided by delta x squared. We're now going to introduce a new constant, which I'm going to call alpha, and this is given by delta t, so I multiply with delta t on both sides. So I can now rewrite the equation, and I will isolate uij plus 1, and this is going to be given by uij, and this is plus alpha times 2 times, it's actually minus, let me just do that properly here, minus alpha times uij, and then we have plus alpha of ui plus 1 of j plus alpha of ui minus 1 of j. Now, if we now try to write this down in terms of a graphical representation, what you would see now is the following. So if we have x along the x-axis, so x here, and we have time along the y-axis, so we would have discretized steps. So we have an x0, x1, and this moves on to an xi minus 1, and then we have an x of I, we have an x of I plus 1, and this goes all the way up to x of n, the last x step. And then we would have a time t0, a time t1, and this goes up to a time t of j, and then we have a new time, which is tj plus 1, and this just continues to the final time somewhere up here, which will be a t of n here. Now, what you see now when we discretize this is the following. So if we now just put in a line here, so let me just give it a different color. So what we know now when we plug in these points, so let's look more in specific at the points which we have here. So the first thing you notice is that in this particular case, when we start with t0 and x0, the points which we have here, they conspire to this specific point here, which would now correspond to a u of t equal 1, but given at a value I, and then it has a t equal to 1 here. So if we repeat the same thing and we move up here, what you would see then is that we have this specific point, this point, and this point, and these 3 points, they conspire to define uniquely the function value at the next point. So this would be our u of I of j plus 1. So what you would have here would be u of I plus 1 of j, the previous time step. The quantity you have here is a u of I j, and then the final quantity here is a u of I minus 1 of j. And if you look at these values which you have here, so this value, that value, and that value, they all conspire to actually give on the right-hand side the final expression which enters the definition of what you have on the left-hand side. So we call this an explicit scheme because all the points previously are explicitly defined. We know the values, And we know the values because we are stepping through time here. And these values here are all known. They are given by the boundary conditions and the initial conditions. So if we wish to mark this now, so let's put some more colors into things here. So what you would have would be something which now is defined by the initial conditions here. So we know the value. So this is given by this function g of, this function g of x, which we have. And then we have, in addition to that, we have the initial conditions. So if we mark them with the value of the function here and the value of the function at the final point, then what we know is that the function values here, so this is just given by u of 1 of t0 of t. That's the boundary condition, and that is given to 0 in our case. And then we would have the same thing here. This would now be given by u of 0 of t, and that's also something which we have given in terms of this Dirichlet boundary conditions. So it means that when we now are stepping up here from the initial conditions and the boundary conditions, so when we are here and along the boundary, we know exactly what the function looks like. And that means that when we start our calculations, then the values which we have here, they are fed into the next time step. And you can see that now if we now set up the differential equation again, the discretized version of differential equation, and we choose the time tj equal to t1, which means that j is equal to 1. What we have then is a u of I of 1, which is simply given now by u I of 0, which is the same as this function g of I, which is our g of x of I. And then we have minus, and if we go back, we have 2 times alpha of u I 0. And we have to be a little bit, for some values of I, we have to be a little bit careful because some of these are defined by the boundary conditions as well. So when I is equal to 0, and when I is equal to the last point, the n, then these functions have to be set to 0. So you have to be a little bit careful here when it comes to the application of the boundary conditions. Plus alpha, and then we would have a u of I plus 1 of 0 plus alpha times u of I minus 1 of 0. And all these functions here, so this is again given by g of I, this is again given by g of I minus 1, and this is given by g of I plus 1. But we have to pay attention that when I is equal to 0 and I is equal to n, then we have to put in the boundary conditions. Then use boundary conditions. Now, this type of equation which you have here, this can be converted into a matrix vector type of equation. And let's now see how we can immediately recognize this as a vector matrix type of equation. So if we now look at the equation which we have, we can rewrite this in a more compact form. So if we now start with I equal to 1, so keep in mind now that for I equal to 0, we know the value that is given by the boundary condition. And if we look at the value of I equal to m, we also know the boundary conditions. So I'm setting up this equation for the unknown values. So that means that what I have then is an equation which will be u of 1. And now I'm looking at a time j plus 1. So I'm not specifying time. I know the values at the initial condition. And this is now given by u of 1, and then I have j minus 2 alpha of u of 1 of j plus alpha of u of 1 plus 1, which is actually u of 2. And then I have j plus u of 0, which is a known value, which is given by the boundary value. So this is given by the boundary. Then I can go to the next value. So I get a u of 2 of j plus 1. That is going to be given a u of 2 of j minus 2 times alpha u of 2 of j plus alpha. And now I have a u of 3 of j plus u of 1 of j. And you can see the pattern here. So I would put I equal to 2 here. You will then continue till I is equal to n minus 1. So remember now that the endpoints are known. Alternatively, if you have a value which is different from 0, you can always insert the values of the endpoints. So there's no problem in doing that, but you just have to be careful when you're now setting up the matrix and vectors which you want to evaluate. So if we go to the second last point, this would be a u of m minus 1 of j plus 1. And this is equal to u of m. Actually, let's keep m minus 1. And then we have a j minus 2 times alpha of u of n minus 1 of j plus alpha multiplied with u of m. And now it's m minus 1. So that means that I need to have m here of j plus u of m minus 2 of j. And you see now that you can recognize this if we define a vector here. So let's call this as a vector u, which is going to contain the unknown quantities. So this would now be a vector and this is a vector of j plus 1. And this will now contain 1 of j plus 1, u of 2 of j plus 1, and all the way down to u of m minus 1 of j plus 1. It means I can also define another vector, which is just u of j. And that would correspond to the quantities which we have on the right-hand side, which are all known because they have been defined by the previous time step. So this is u of 1 of j, u of 2 of j, and all the way down to u of m minus 1 of j. So this quantity here is unknown. And this quantity here is a known quantity. Now you can now write this two quantities in terms of this unknown vector u of j plus 1 in time. And this is given by u of j multiplied with a matrix A. And this matrix A is nothing but, when you now look at what we have here, so what you will see is that you have only, if you go back to the differential equations, you see now that what we have is something along the diagonal. So these would be the elements which you see here. These two elements are elements which we would have along the diagonal of the matrix. And these would now be non-diagonal matrix elements. You see that clearly when you look at here, we have a 2 here, a 2 here, and then we have 3 here and 1 here, and the same here with 2 and 0. So there's going to be a constant alpha, and there's going to be a 1 minus 2 times alpha. So we can actually rewrite this now in terms of a matrix which has 1 minus 2 times alpha. And then along the diagonal, the non-diagonal, we're going to have alpha. So we will have 1 minus 2 times alpha along the diagonals. 1 minus 2 times alpha is going to be an alpha, an alpha. So these are all going to be equal. And then we will have zeros else. And we can rewrite this in terms of the identity matrix. And then we have an additional matrix, which we're going to call a matrix or matrix B. So minus 2 times, sorry, not 2 here, but times alpha times a matrix B. And this matrix B is now defined as 2 along the diagonal and minus 1 along the non-diagonals. Now, since this is an equation which is now being repeated again and again and again, we could start with the first value, which is j equal to 1, first time step. This is actually a multiplied with u0, which is defined by the boundary conditions and the initial conditions. And what you see now is that this u of a given value j is actually the repeated action of this matrix to the power of j multiplied with u0. So this reminds us quite a lot about what we normally call a Markov chain. And one of the reasons why the diffusion equation is so popular is that you can actually also link that, you can derive it from the mathematics of a Markov chain. So what you see here is actually something which is pretty close to what we normally have in the definition of the Markov chain, that the equation is just the next time step is just defined by the previous time step. Now, this matrix is a tridiagonal matrix. So this is tridiagonal. Now, to perform this matrix vector multiplication in this case is actually a waste of CPU cycles. And the reason for that is that if you perform blindly a matrix times a vector multiplication, and if the matrix is of dimension n times n, and the vector is dimension n, this normally goes like n squared floating point operations. And that is definitely a waste of CPU cycles because you have lots of zeros. So this matrix here has, except for the diagonal and the 2 non-diagonal matrix elements, this matrix here has only zeros. So that means that the efficient way to implement this is simply to have a loop over I here. And then for when you loop over I, you simply perform the different multiplications. So you would see now if I goes up to n, roughly, n minus 1 in our case, you have, in this case, you have 1 subtraction, 1 multiplication. So if we now think that the floating point operations are treated in a democratic way, in the sense that they all take the same time, which is not exactly true, but you have 1 floating point operation here, 1 multiplication here. It's actually 2 times alpha. You would define a variable there, so that you just perform this multiplication once. So you have 1 flop here, 1 floating point operation here, so that's 2. You have an addition here, that's another floating point operation. So you have 3 floating point operations, and you have a floating point operation here, so that's 4. And then you have a multiply, so that's 5. So it means that if you sum this up, if you now don't look at memory writes and memory reads, because for every one of these, you also need a memory read here. And then you're writing to memory when you do the update. But in principle, you have 5 floating point operation for each value of n. So that means that when you step this through the matrix here, since it has roughly m elements, so you have 5 times m floating point operations. And that is much less than if you have a matrix of dimensionality m times m, then you would end up with m squared floating point operations. So this is clearly a more efficient way of actually doing this, and it saves you a lot of CPU cycles. Now, one of the drawbacks with these methods is, so it's extremely simple. So this is the forward Euler method. So one of the drawbacks here is that it has a very strict stability criterion. And I'm not going to derive it, but you can find this in basically all textbooks on partial differential equations. And you will also find it in my lecture notes on computational physics, is that there is a very tough requirement here, so that delta t divided by delta x squared cannot exceed a half. If you violate these conditions, the equations will be unstable. And after some few time steps, the solution will simply explode. So that means clearly that if you now choose, suppose a very small time step in delta x, suppose delta x is 10 to the minus 2 here, then what you see then is that delta t becomes very small. So it has to be smaller or equal to a half times 10 to the minus 2 squared. Sorry. So if we multiply that one, the number of, so if you take delta t, what do they? So let me just rewrite this one. So you would have a t of minus 2 to the power of 2 here. So that means that your time step has to become very, very small. And this leads to an algorithm which is easy to implement, but it has a very strong requirement on the values of delta t and delta x. So the forward Euler scheme is easy to implement, but it leads to a scheme which has a clear limitation in this strong condition on delta x and delta t. So this leads to what's normally called the implicit scheme, which we are going to look at after the break. And that will be the second scheme, which you should feel free to, if you want to implement and study in conjunction with the solution of neural networks. So we are just 1 minute over time here, and I thought we could put on a small. Now, when we looked at the solution of the partial differential equation in the previous lecture, we looked at an approximation to the first derivative with respect to time, which led to what's normally called Euler's forward scheme or forward-going scheme. Now, the implicit scheme, on the other hand, takes into account the different approximation to the Euler's method, which leads to something which is called the backward stepping Euler approximation. And everything is rooted in two ways of doing this Taylor expansion. So when we now look at a Taylor expansion of a specific quantity, so we have a quantity x plus, let's say, a delta x here, we can now, instead of having plus a delta x, we can have a minus delta x. And in that specific case, what we end up with is a Taylor expansion in terms of u of x, but then we're going to have a plus minus delta x. And this is given by the first derivative with respect to x. And then we have the second derivative, which obviously becomes positive, divided by the factorial, second derivative, and plus plus. So if you now take the minus sign instead of the plus sign, this is going to lead to what's called Euler's implicit scheme, or the backward going Euler, or just simply the backward Euler. It doesn't mean it's a backward algorithm. Actually, it's a better algorithm because it leads to a scheme which is stable for all combinations of delta x and delta t. You have, however, to keep in mind that if you make a delta x and delta t very large, your truncation error is also going to be pretty large. So the backward going scheme assumes then that we would then write du dt, and we are going to approximate that one with a u of I of j minus u of I of j minus 1 divided by delta t here. So that means that when we are setting up the differential equation, what we have then is an equation which is now going to depend on the previous time step. So we will have something which runs like a u of I j, which is equal to u of I of j minus 1. And then we multiply with delta t again, as we did before. So we're going to have a plus an alpha, and then we will have u of I of plus 1 of j plus u of I minus 1 of j minus 2 times alpha of u of I of j. Well, alpha is the same as before, which is actually delta t divided by delta x squared. Now, in this equation here, we have now the result at the previous time step, but we have three undefined values, which are actually the values of the function at u of I plus 1, and u of I minus 1 at the time step j. So what we end up with doing now is to reshuffle the unknown quantities. So the unknown quantities now are given by this quantity, obviously this quantity here, this one, and that one. So we will now reshuffle everything in terms of known and unknown. So we will have the unknowns on the left-hand side, and then we're going to have the known quantities on the right-hand side. So the known quantity is actually uij minus 1. And now you could think at starting at j equal to 1, for instance, and that means that the ui of 0 would then be defined by the boundary conditions and the initial conditions. Now what we have then is a new uij, which now is given by 1 plus 2 of alpha. So instead of 1 minus 2 alpha, which we had in the explicit scheme, and then we're going to have a minus an alpha, and then we have a ui plus 1 of j plus a ui minus 1, minus 1 of j, and this is equal to u of I j minus 1. And now you can see that this algorithm, if we start at j equal to 1, what we have then is just a u of I of 1 plus 2 alpha minus alpha of u of I 1. So we would have a u of I plus 1 of 1 plus u of I minus 1 of 1. And this is equal to u of I of 0. And this quantity which you have here, this is a known quantity. This is given by the boundary conditions and the initial conditions. So it means that when we try to describe this graphically and go back to the same situation which we had for the explicit scheme, we had an x of I minus 1, we have an x of I, and then we have an x of I plus 1. And then we are looking at a t of j, and then we have a t of j minus 1. So if we now look at the points which we have, and let's just mark it a little bit better here. So if we look at these points which we have, what we have now is that we have three unknown quantities, and they are now only defined by one quantity. So when we look at this value here, which is ui of j minus 1, that needs to define u of I plus 1 of j, and this is u of I of j, and this is u of I minus 1 of j. So what we see here now is that we have only one quantity to determine three unknown quantities. And the same thing happens if we start at t equal to 0. And that means that we have the boundary conditions and the initial conditions, but every boundary condition and initial condition, or every value at the boundary and at t equal to 0 is needed to define three new points. So that means that we have what is normally called an implicit scheme, that we will have to define implicitly the next time step. Now, if you look at what we have here, this equation, this can also be rewritten in terms of a matrix times a vector. So we would still now define a vector, which is u of I or u of j minus 1. So that will contain the quantities u of 1, of j minus 1, u of 2 of j minus 1, and all the way down to u of n minus 1 of j minus 1. And similarly, we will have the unknown quantity, but we can now rewrite that. So if we take the unknown quantity u of j, so that is going to be the new vector. This is given by u of 1 of j, u of 2 of j, and all the way down to u of n minus 1 of j. And remember now that since we have the boundary conditions and the initial conditions, we are not specifying u of 0 for x and u of 1 for x, the two endpoints. Actually, it's u of n, because we have n discretized steps in the x direction. Now we can now rewrite this in terms of a new matrix, which we are going to call an A tilde times the vector u of j, and this is equal to the vector u of j minus 1. If you now look more carefully to what we have, so let's just go back and look at the equation here. If we now look at the equation, you see that we have a plus 2 alpha, but now we have a minus alpha here times the non-diagonal matrix elements. If we go back to what we did with the explicit scheme, so let's just scroll back a little bit, you saw now that what we did was to define a matrix A, which was 1 minus these 2 alphas. Now instead what we have now is a plus a 2 alpha, and we have a minus alpha. So that means that we can actually rewrite this new matrix in terms of what we did before. So instead of having a plus a minus alpha, we actually get a plus alpha. And we can keep the same matrix as we have here. So the only thing we need to do is to redefine this matrix, A tilde. This is actually, this matrix A tilde is simply the identity matrix plus alpha times this matrix B, where this matrix B was simply given by 2 minus 1 along the diagonal, the non-diagonal, and 2 along the diagonal. Sorry, minus 1, minus 1, minus 1, and minus 1 here. So we have a diagonal which contains 2's, and then we have the non-diagonal which just contains minus 1's here. So it's the same, the matrix B is exactly the same. Now, this is a matrix. It's actually a linear algebra problem which we are solving here. And you can solve this linear algebra problem by using something which is called the Thomas algorithm. You would never calculate the inverse of the matrix, because if you're calculating the inverse of that matrix, that would lead to something which is, if this matrix has a dimensionality m times n, this would give you n cubed floating point operations to calculate the inverse of a matrix. Now, by setting up an algorithm which is called the Thomas algorithm for solving this set of linear equations, you end up with, for this specific matrix, something which runs like 4 times m. M is the dimensionality of the matrix, floating point operations. So this is normally solved by using something which is called the Thomas algorithm. So this is called the Thomas algorithm. And that requires something like 4 times m floating point operations per second. Floating point operations. And this is a very efficient algorithm. So you could obviously invert a matrix, but that leads to an algorithm which would require m cubed floating point operations. And that's highly inefficient since you're doing this for every time step. So the algorithm which we have here is very easy to implement. and it's stable. It gives stable results for all delta X and delta T combinations. Now, the error which you have here, so error in time runs like O of delta T, and the error in X runs like O of delta X squared. If you add an additional spatial dimension and you want to add the Y direction, you would have a similar error in the Y direction, which goes like delta Y squared. Now, you can combine the implicit and the explicit schemes into something which is called the Crank-Nicolson scheme, and that allows you to get an error in time, which goes like delta T squared. And the Crank-Nicolson scheme is one of the standard schemes which is being used in the solution of these types of differential equations. So in project number 2, what we have been calling the standard path, then the idea is actually to use the differential equations so you would actually have to you would invert this only once, but the thing is that the inverting the matrix is much more expensive. So that is correct. So you would actually invert the matrix in the first time step, because then you have just a matrix you would keep multiplying it with. So if you do many more time steps than the size of the matrix, maybe at the end, matrix inversion could result in less floating point operations. But normally what you would do is actually to solve these equations here for every time step, but by using the Thomas algorithm, which is very cheap to implement. So the only thing which changes then is obviously, if you use a Thomas algorithm, you would have to update the right-hand side every time, because the right-hand side changes. But the Thomas algorithm is much, much simpler to implement than doing a matrix inversion, which in this case would run like n cubed floating point operations. So you have to do quite many time steps in order to match the Thomas algorithm. So that's correct. You would only invert the matrix once. Thanks for the comment. The thing which I wanted to go back to now is the calculation of this or the solution of this type of equations using neural networks. And in the lecture notes, there is an example where we compare the solution with Euler's explicit scheme with the solution from a neural network. And what you will see then, that this neural network is very simple. And this is where I would normally recommend that you would use software like TensorFlow or PyTorch, which gives you much more flexibility in studying the solution of partial differential equations. So before we move on to convolution neural networks, I wanted to end this part, which has to do with the partial differential equations, by looking at the way you would set up the solution of the diffusion equation. So what you will find here is a repeat of many of the things we went through with the slides here. And you will recognize the same machinery which we did, with examples on how to do the explicit scheme. There is also discussion on the stability of these equations. And you can actually, in these lecture notes, you will find the derivation of the stability condition. And as I said, the stability condition for the explicit scheme is given by delta t divided by delta x squared. So I haven't gone through the calculation of the stability condition, because this is also detailed in the lecture material here. So if you want to look at that, you can find more details in the lecture material. And similarly, you will find the derivation of the implicit scheme and the stability condition for the implicit scheme, and how you can encode it. And then if you prefer to use the Crank-Nicolson scheme, you can actually do that. And that would give you a truncation error in time, which goes like delta t squared. And you will find the mathematical details in the lecture notes here. So that would be the first part of the project. And then the second part deals with the setup of the differential equation solver using a neural network. And you will find examples of how you can do that. And again, what you would have would be the difference, a function which depends, function f, which defines your cost function, which is now the difference between the left-hand side and the right-hand side. And in this particular case, your function would depend on the derivatives with respect to x, also the derivatives with respect to time. So it means that one of the things you need to set up then is actually the Jacobian. So that you need a partial derivative with respect to x and t. And the details which follow in the slides here are related to the solution of the diffusion equation. But the basic principle when you're solving differential equations with neural networks is that you take the difference between the left-hand side and the right-hand side of your differential equation, given a certain trial function, which contains your initial and boundary conditions, and the neural network, which is then the part of the solution which is going to find the optimal way to represent the wave function. So in the beginning here, you will see the typical problem, and this is basically what that project number 2 deals with. And you define the problem. These are the same things which we went through. You can set up, the code example here sets up the neural network using autograd for taking the derivatives. So this is very similar to what we discussed before. And you would then, after you set up the network, the basic parameters, you would have some kind of a trial wave function. And you would have a function now which contains both the time dependence and the spatial dependence. And there is a trial function here, which we assume now should obey the boundary conditions. So we have a specific boundary condition here, which goes like a sine of pi of x. You need to set up the Jacobian. So the Jacobian is used because the program must find the derivative of the trial solution with respect to x and t. And this gives the necessity of computing the Jacobian matrix, as we want to evaluate the gradient with respect to these variables. Note that the Jacobian of a scalar value multivariate function is simply the gradient. Just keep that in mind. So in autograd, if you use that, which is normally what we would recommend that you do, the differentiation is by default done with respect to the first input argument of your Python function. And since the points in an array representing x and t, the Jacobian is actually calculated using the values of x and t. And to find the second derivative with respect to x and t, the Jacobian can be found for the second time. And the result is a Hessian matrix, which is the matrix which contains all the possible second order mixed derivatives of the function g, x, and t. So just keep that in mind that you, in this specific case, you need to deal with the Jacobian. And the example here is just tailored to this very simple function. And when you are setting up using autograd, you can actually easily find the Jacobian and the Hessian matrix. And in this specific case, there is also an analytical solution to the problem. So it means that we are going to let the neural network try to explore the parts which we don't include in the boundary conditions and the initial conditions. And the results of the calculations, so after you set up the neural network, actually not that impressive with this simple neural network, which I have here. So you end up with a final cost function, which is the difference between the left-hand side after a given number of iterations, which is not impressive. So my network is not a very deep network. And it also has a difference between the analytical solution and network, which is still pretty large. And you can see the plot of the wave function here. this will be the plot which results from the deep neural network. You would have the analytical solution here. So they look very much the same, but there's still quite some difference. And this would be the solution which you would get. The final one, this is the one which you see here, is actually a difference between the analytical solution and the neural network solution. So it means that there's a lot of room for improvement here. And that's why I normally recommend using software like PyTorch or TensorFlow in order to solve this type of equation, because they give you much more flexibility in setting up the neural networks and making a deep neural network. But you have to define the cost function in terms of the different partial derivatives and the difference between the left-hand side and the right-hand side, given a trial wave function or trial solution to the differential equations. So this basically sets the scene for one of the paths in project number 2. Now, what I wanted to use the rest of the lecture today is to get started with a discussion of convolutional neural networks. And we will continue that discussion next week. And this, I believe, is something which is of great interest for the research topics of many of you, since many of you will end up dealing with images. On the other hand, for those of you who will go in a direction dealing with differential equations, this is something which you can think of looking at, because partial differential equations, is in particular multidimensional partial differential equations. There is more and more research now on using deep learning methods to solve these types of equations, in particular if you're dealing with high-dimensional partial differential equations. So a typical example is solving the Navier-Stokes equations for turbulence, because in turbulence you often have to have a very fine grid in order to be able to simulate properly. So what I'm going to do now is just to switch back a little bit to my slides, and then we are going to look at the basics of a convolution neural network. So let's just bring up the slides here. So let me just go through the slides and pass the topic which has to do with partial differential equations. I should actually have put up the right starting point here. There's a lot of material on differential equations, but I wanted to give you the kind of overarching idea of convolutional neural networks first. So this is a very, very hot field, and nowadays convolutional neural networks are really a central element in what you might call the kind of spectacular success of deep learning methods. So the trick behind convolutional neural networks is obviously that they use the mathematical process of convolution. If you think back to what we did with a neural network, what we had then was we started with an input layer, and that input layer was connected to the nodes in a hidden layer. And then we could have more and more hidden layers. Now, a standard feed-forward neural network is something which we call a fully connected network. It means that the network is tailored so that you have a matrix containing the weights, which is multiplied with the vector defining the hidden layer, or a matrix defining the hidden layer. And the matrix is dense, and we perform dense affine transformations, which means that if you have lots of input variables, then the dimensionality of the problem quickly becomes huge. A convolutional neural network is actually a way to reduce the dimensionality of the problem by the process of convolution. So you can think of, if you wish to take an overarching view on a convolutional neural network, you can think of this as a way to reduce the dimensionality of a standard feed-forward neural network, where you're dealing with dense matrices. So that means that we are going to select only some of the features from the input. So if you think of you recognizing houses, the thing which is important for a description of a house are obviously the corners, it's the roof, it's the windows and the doors, but you don't need to carry with you all the information about the color of the house. Because if you think of a house, I mean, of a given color, a pretty large part of the house, which is not defined by windows and doors, will just be exactly the same. It will have the same color. And that's some type of information which is not that necessary to carry with you in its full details. So it means that in that specific case, what you could do now is to filter away some information. So convolutional neural networks means that you have some filters which reduce the dimensionality of the problem. And but many of the same basic things which we have seen before, like the backpropagation algorithm, is also implemented in convolutional neural networks when we are learning the weights and the biases of the filtering itself. So we are coming back to some of these things, but let me first go through some of the basic and overarching views on a convolutional neural network, and then we're going to dive into the details. So this is really much tailored to images, where you have some specific features which pertain to a given image, like a house. You would have the corners, you would have the roof, windows, and doors. And that's the type of information you actually want to keep with you. So if you think of a neural network, we would define them as normally what we call affine transformations. That is, a vector is received as input and is multiplied with a matrix of so-called weights or unknown parameters. And that produces an output to which a bias vector is usually added before passing the result through a nonlinear activation function. So it means that we keep the full dimensionality of the problem. So this is applicable to something you would apply to any type of input. It could be an image, a sound clip, or just an unordered collection of features. So a CNN is something which now, as I said, allows us to reduce the dimensionality of the problem. So when you consider now an image and many other similar kinds of data, these data have normally an intrinsic structure. They often share some kind of common properties. They would typically be stored as multidimensional arrays. So if you think of the pixels of a figure, like the MNIST dataset, which we looked at when we were discussing the feed-forward algorithm, which we developed just some weeks ago, then we had an image which was defined by 8 × 8 pixels. So we had 64 pixels in total. They normally features one or more axes for which the ordering matters. So you would have the width and the height of an image, the time axis for sound clip, and one axis, which is normally called the channel axis, is used to access different views of the data. So you could have the red, green, and blue channels of a color image, or left and right channels of a stereo audio track. So these properties are not exploited when you have a standard feed-forward neural network. So what we do then is that we treat all the axes in the same way, and the specific topological information is not taken into account in the procedure. So you can now ask yourself, I mean, what if I would like to take into account some of these properties? So in principle, then if you're looking at convolutional neural networks, this is a way to actually keep track of some central features and just leave out some other details. So a discrete convolution, which is a kind of filtering, is a linear transformation that preserves this notion of ordering. It is sparse. There are only a few input units which contribute to a given output unit, and it reuses parameters. And the same weights are applied to multiple locations in the input. And we will see these details as we move on here. Think of the example which we went through when it came to the MNIST data set. If you look at an image which has 32 times 32 pixels, which is still a pretty coarse image, you can have something like 3 color channels. So it means that the fully connected neuron in a first hidden layer of a regular neural network would have something like 3,072 weights. This is quite a lot. It's still manageable, but clearly this fully connected structure does not scale to larger images. So if you want something of a pretty high resolution, you could do a 200 times 200 pixels, and that would give you something like 120,000 weights. And we could have several such neurons, and the parameters would add up quickly. So clearly this kind of full connectivity is wasteful, and the huge number of parameters would quickly lead to possible overfitting. So suppose now you have an image of a house, which is has a red color, and you have 200 times 200 pixels to identify or to represent this image. Clearly, many of these pixels will just be used to represent some parts of the house which have a red color. Whereas the things which would be interesting in order to classify the house would just be the corners, the roof, and the windows and the doors. And then we could be a little bit more lax when it comes to the types of colors which we have, because it's just one color. So convolutional neural networks, they take the advantage of the fact that the input consists of images, and they could try to constrain the architectures in some specific way. So these convolutional neural networks, they have often been trained to specific types of images. So if you're dealing with facial recognition, they have been trained on hundreds of thousands and millions of pictures of humans. If you're dealing with houses, it's the same. And you have huge data sets like ImageNet, which is a very popular data set, which contains just simply millions and millions of images to which you have pre-trained neural networks. So it means that you have a pre-trained network, and if you want to recognize faces, then you have trained a network on recognizing millions and millions of pictures in the database. So the way we are going to look at this, and the way we're building up a convolutional neural network, is by some different types of processes. And the types of processes you have when you're setting it up is that you obviously have your input layer. So you could have the raw pixel values of an image. And in this case, you have an image with width 32 pixels, height 32 pixels, and it has 3 color channels. So this would be the dimensionality representing that specific image. Then the first thing you do now is that you filter through some specific features. And this is normally called the convolutional layer. And you can use some specific filters, and these will have parameters, the way you set up the filters, the optimal filter. And that means that the parameters you end up with in the back propagation algorithm, they are the parameters which represent the specific filters, which gives an optimal representation of the image which you're looking after. So if it's a house, you will train it on corners, the roof, and the number of windows and doors which the house has. So the convolutional process is something you can think of as a filtering using the mathematical operation of convolution. Then, when you've done that, there is because you have produced a new data set which has been propagated, and then you would let that go through a ReLU layer where you produce an output from the convolutional layer. Then there is something which is called a pooling layer that performs a further downsampling of the spatial dimension. So you can actually reduce the dimensionality of the problem by that way. And then when you're done with that one, you can then have a fully connected layer, will compute the class scores, resulting in a volume size, which can be even smaller. Or you could now think of, and this is quite common, is that you have a mix of convolutional layers and normal feed-forward layers. So that means that you perform a convolution and reduce the dimensionality, and then you have a standard neural network in which you perform the additional training, because then you have stripped down the dimensionality of the problem so that you can actually run a standard feed-forward neural network. That's another possibility. So when you transform the images, so what you can think of this convolution neural network transforms the original image layer by layer from the original pixel values to the final class scores. Some layers contain parameters and other layers do not have parameters. So the convolutional layers perform transformations that are a function of not only the activations of the input value, but also the parameters, which will be the weights and the biases. If you then look at the ReLU and the pooling layer, which we will describe in more detail soon now, they will implement just a fixed function. You could think of that as a parameter, but in this case, there is no training element. You just use a fixed function to perform this further reduction of the dimensionalities. And then you can have a standard feed-forward layer, but you can also have a so-called flattening layer. And the parameters in these layers, they are normally trained with a standard gradient descent, so that the class scores that the CNN computes are consistent with the labels in the training set for each image. So in brief, what you have is that a CNN architecture, in the simplest possible case, it has a list of layers that transforms the image volume into an output volume. There are a few distinct types of layers which you can repeat again and again and again. So it's a convolutional layer, there's a ReLU layer, and there's a pooling layer, which we will describe in more detail soon. And each layer accepts an input 3D volume or 2D volume. Each layer may or may not have parameters. So the convolutional layer has, the ReLU pooling layer does not have. And each layer may or may not have additional hyperparameters. So the convolutional layer and the pooling layer can have hyperparameters, but this ReLU layer, where you simply produce an output with an activation function, does not have additional hyperparameters. There's tons of available lecture notes, and what I normally recommend is actually the chapter 9 in the textbook of Goodfellow, which is actually a very good textbook. We have lecture notes at the University of Oslo on a course which is called IN 5400, which is actually machine learning tailored to image analysis. And this is normally a course which is highly recommended if you want to specialize in imaging and using machine learning on imaging. So the key idea is, if you think of a standard neural network, that is represented by an affine transformation. The key idea in a CNN is that in images, neighbor pixels tend to be related. So we connect only neighboring neurons in the input instead of connecting all with the first hidden layer. And we may perform a filtering, which where convolution is the mathematical operation. So what I wanted to say something about next time is actually the mathematics of convolution. I see we have only 2 minutes left. So we are going to start with the mathematics of convolution next week. And then we are going to go through the basic buildup of a convolutional neural network. And the way we're going to do that is to use TensorFlow and its API on top of it. The API is called Keras, K-E-R-A-S. And it's a very useful API, which allows us to set up a convolutional neural network in a very flexible way. And we are going to discuss these details. So I invite you to take a look at some of the slides here till next time. And then we are going to go through the basics of a convolutional neural network. And after we're done with that, we are going to look at another very popular type of neural networks, which are so-called recurrent neural networks. And when we're done with that, we are going to look at some unsupervised learning methods, and that will conclude the part on standard machine learning approaches. And when we meet physically on March the 7th, we should also try to discuss possible paths after we are done with the deep learning path. And one of the possible approaches is actually to look at the Bayesian statistics and Gaussian processes, which are very popular methods in order to be able to, for instance, estimate errors properly, and also to develop probability distributions which describe our data. But these are things which we can discuss in more detail when we meet on what kind of paths we should take when we are done with the standard machine learning part. So I'm going to stop the recording now, and then we meet again